lunch is by Ryan Thorngren from Berkeley. So he's going to tell us about symmetries of Chern-Simons theory.
Thanks for the introduction, and thank you to the organizers for such a stimulating workshop. It's very great to be here and have a chance to tell you all about some cool physics. So I'm going to tell you today about symmetries and lead you into this idea of higher symmetry. Okay, so we'll also give some examples. So a symmetry, I'll remind you, is an operator acting on Hilbert space, commuting with the Hamiltonian. Symmetries tend to come from currents. So here's a formula for one of these operators given as an integral of local operators. And we can take the commutator of O with H, and then using the fact that H generates time translations, that's pulling a time derivative into this integral. And if we write the covariant current, where we dualize this vector to a 3 form, so here I'm using 3 plus 1d notation, but you can do this in any dimension, of course. You just have a different number of indices. Your vector current will dualize to a form of degree the space dimension. So here, 3 indices. You have to have this root g here so that it becomes a 3 form. And then the way to write this equation is just to say dj equals 0. So this is a wonderfully compact way of writing that j generates a symmetry. OK, so this is how I'd like to interpret Noether's theorem, that symmetry equals topology. Right? So if we have a closed form, our form is closed if and only if it's conserved, if and only if j generates a symmetry by integrating over some spatial slice to get an operator. OK, so if I have some spatial slice here, and now I integrate instead over a 3-cycle that is transverse to the spatial slice. So here I could have O is the integral of j over this thing. Then in a time slice, it will look like I have domain walls. That will be the place where my integration cycle intersects the spatial slice. OK? So why stop here? Suppose we have a 2 form. We can also form an operator by integrating this 2 form over any surface. And if we measure this operator at a later time, so you can sort of imagine this picture where we integrate j here, get O, and we integrate j here to get O prime. And now the difference between these integrals is the integral of dj over the cylinder. So again, we get that this operator commutes with the Hamiltonian if dj is 0. We can get the converse direction also by an Einstein-style argument where we just change our reference frame and find that the derivatives in the other directions have to be 0. So you get another thing where O is a symmetry if and only if dj equals 0. OK, so now if we do the same thing here, we make our integration surface transverse to the time slice, then we're going to have something that's codimension 2 in space. So instead of these domain walls, we'll have point-like domain defects. So these kinds of things are what we call a higher symmetry. So for example, in Maxwell Theory, df is 0 by virtue of having a gauge field, and d star f is 0 by the equations of motion. And there are interesting things that you can say about this symmetry. One of them is spontaneously broken. There's some like emergent symmetries that happen when you have matter as well. I refer you to this paper by Davide, Anton, Nati, and Brian. Yes?
Do you have an understanding of this in, say, a lattice model with a local Hilbert space on each side?
Of the Maxwell theory?
What?
Of Maxwell theory?
No, just the higher symmetry.
Absolutely, yeah. So in this paper of Anton and my own, called Higher Symmetry and Gap Phases of Gauge Theories, we talk about like SPTs, and we give a lattice model for all those SPT of a Shi-Chen style. I won't be talking about lattice models, but we can talk afterwards about it. Okay, so anytime we have a codimension 1 operator that is topological, we have a symmetry. So if we have a codimension 2 operator that's topological, we can also try to interpret that as a symmetry. And one theory that has lots of topological line operators, so now we're down to 2 plus 1D for a little bit, is Chern-Simons theory. Right, so U1 level K has K electric operators, these charges. They're Wilson lines. They are insertions in the path integral of something like this. P is only defined in Z mod K. Because of the Chern-Simons action, you can cancel this with P equals K by a large gauge transformation. Okay, another example, Digraph-Witten theory has both charge lines and flux lines. We just heard about. A general Chern-Simons theory has some more complicated structure to its category of line operators. The invertible ones describe discrete symmetries because these categories only have finitely many simple objects. And yeah, you can add them together. You can't have like half of one in this one. Okay. So if I have a state made from computing the partition function on a handle body, which is how I normally know how to write states. So suppose I fill in this torus in such a way that this circle bounds a disk. So this is a solid torus. And I perform the path integral over this solid torus. I'll get some state on the boundary. And now if I apply one of these line operators, which means threading a flux through this solid torus, I end up in a different ground state. So this means that if I apply my operator to my ground state, I'm getting a different ground state. So this is the statement that the symmetry is spontaneously broken, where here I'm being a little bit, I'm overstepping myself a little bit in saying spontaneously, because this theory doesn't have anything but ground states. But if you imagine adding some dynamics to it, here we're seeing that the symmetry is acting non-trivially on the ground states.
You want to say that the ground state depends on spin structure?
This is not spin structure.
No symmetry, current, which is this one.
So this will work even in the K-even case, where we don't have any spin structure dependence. And this will actually account for all of our ground states. Right? At least for U1 level K, the ground state degeneracy on a torus is K, and we get them all by threading different of our K line operators here.
Different sectors of the theory. Nothing to do with spontaneous symmetry in the usual sense.
Yeah, so I'm trying to convince you that there is a generalized sense of spontaneous symmetry breaking, where you may as well call the up state of an Ising magnet a different sector than the down state of an Ising magnet. But they could both evolve from the same microscopic theory. Which they do, right?
Since the state is degenerate, the system may choose to be in a given state.
Right. And it does so, however, we don't, it's beyond our understanding. But it's all in the entropy. Right, so the ground state degeneracy should be proportional to the number of symmetry generators. But here, this is a very weird quantity to think about, like, in terms of symmetry generators. How can a spontaneous symmetry account for ground state degeneracy that depends on the topology in this way? So I have a puzzle for you, which is, suppose I have an Ising model on the blackboard, and I have 3 blobs where the temperature is less than the critical temperature. And then I have everything else. The temperature is above the critical temperature. How many ground states? Anyone?
You mean by ground state when you measure temperature during an excited state?
Well, I mean, like how many? So I'm trying to say like classical statistical mechanics. Like how many sectors of the theory? How many Gibbs measures are there? Well, you can choose up or down in each one, right? So we have 2 times 2 times 2. So here, our maps from our space, which here is really like disconnected, only have to be locally constant into our group. So here we get a topological ground state degeneracy, although it's kind of the most boring kind, because it only depends on the number of components, but still it depends on the topology of the manifold. So even ordinary symmetries, spontaneously broken, give you topological ground state degeneracy. Okay, and another way of writing this, the space of these ground states, is to say it's h upper 0 of these 3 blobs with coefficients in Z2, our symmetry group. Okay, h upper 0 is just your set of locally constant maps. Okay, so how could we have something that counts like k to the g? Any guesses? Well, we should just take that 0 and make it 1. Yeah. Okay, so h upper 1 x z mod k is a natural guess, judging from this. These are maps not from x to z mod k, but maps from x to a space called bz mod k. I like to call this, therefore, a bz mod k symmetry. Bz mod k is something 1 category level above a group. It's a 2 group. 2 groups have 2 ways of multiplying. And this makes sense if we have codimension 2 operators. So if I'm drawing a space picture, we have 2 point-like operators like this. And we can either multiply from in this horizontal direction, or we can multiply in this vertical direction. And you'd say, oh, well, these operators are topological. These are the same multiplication. But let me remind you that when you go from one multiplication to the other, you really pick up a phase. And if you go all the way around, you pick up the braiding phase between these 2 quasi-particles. So they really are 2 distinct multiplications. They're homotopic, but not trivially so. So here I meant not trivially so. Okay, and similarly, if we have codimension k, there will be k directions along which we can compose our operators and some kind of coherence among all those directions. Okay, well, this predicts the wrong number of ground states, right? It predicts k to the 2g ground states when we only have k to the g ground states. So somehow, over here, I'm not allowed to apply my operator around this loop because this loop encloses a cycle. What's going on is there's some kind of anomaly where if I apply one of these operators and then the other, and then do them in the opposite direction, the difference between those is this linking phase, which for Chern-Simons theory with 2 Wilson loops is non-trivial. And so this is telling me that the 2 line operators don't commute, which means I can't simultaneously diagonalize them to get consistent quantum numbers. So I'm not going to get a ground state degeneracy that is proportional to the size of the whole group. It's kind of like a non-abelian group. You get ground state degeneracy that is like the largest commuting subgroup. Okay, so this is going to be a kind of Twift anomaly. For continuous symmetries, this kind of anomaly affects the counting of the Goldstone modes. If you have like chiral symmetry in 1 plus 1D, left movers and right movers, and you spontaneously break both symmetries, find only one Goldstone mode. Here, it affects the ground state degeneracy. Okay, and you can analyze what the typical splitting on a finite size system will be just by asking what is the typical action of the process of like including this loop. And since it's a line, the action is a one-dimensional integral, so it scales like L, and the only other length scale in the problem is the correlation length. So, yes?
To get this either minus L over C, you need to add like a Maxwell term to your Chern-Simons theory?
Well, I'm just supposing, my argument is just that these line operators are one-dimensional, and the only length scale is the size of the system and the correlation length.
I guess I'm saying the only way your higher symmetry is exact is if C is 0.
Or L is infinity.
But I
mean, spontaneously broken symmetry only happens at infinite system size anyway. My symmetry remains exact at finite system size.
I don't think you can have an example of this higher symmetry without C being 0.
So let me remind you that Maxwell theory, if I add a Maxwell term, it will be, well, I'm going to get to how it acts in the fields in a second, and you'll see that if I add a Maxwell term, the Maxwell term will also be symmetrical under this transformation. But it is a good good gripe to have. Okay. Inspired by this, okay. Going to try to guess the symmetry action on the fields, just knowing what the generators could be. So the generator is a element in it's a cohomology class of closed Z mod K1 forms, and I can equivalently express those as certain gauge fields. So lambda will be a gauge field, so that K lambda is trivial. Of course, that means gauge trivial. So K lambda is d phi for some UN scalar phi. And once I have lambda, well, I may as well just try shifting A by lambda. Okay, and so I analyze the Chern-Simons action. The proper way to think about this action is not as a three-dimensional integral, but as a four-dimensional integral. We can always choose some four-manifold that bounds our space-time, and then perform this integral on it. And further, we can do some finagling in finding an extension of lambda. Lambda's flat, but we can't necessarily extend it so that it's flat, but we can extend it so that this Z mod K-ness remains. And then when we compute the variation of this action up in 4 dimensions, the first term is an integer, is a 2 pi integer, so it drops out. And the second term, k d lambda, now we use our expression that k d lambda is exact, and then integrate by parts and get 0 there. So this is a symmetry of the action. And now, Mason, you'll observe that shifting A by a flat connection does not change F. So a Maxwell term is also preserved.
Initially, wouldn't convert to Hamiltonian.
Well, these are, I don't know, somehow in, yeah, so perhaps at finite system size with a Maxwell term, I need to modify that expression of the loop operator. This is the expression of the symmetry that I would always choose to use. And this is how the symmetry is going to act in Maxwell theory as well. So perhaps you're right, and then the Wilson line is not actually the symmetry generator when we have a Maxwell term, but some local modification should work.
Generalize this line operator to something which generates this shift.
Right. Yeah, and so you can. This is a this is like a K flux, so it just happens like that with the Chern-Simons, like K flux and Wilson line are the same, but with Maxwell term, they're no longer the same. Okay, so we have a symmetry of the action. Under this symmetry, the Wilson line transforms. So the proper thing, I guess, to say is that the Wilson line is not the symmetry generator, but it's actually the order parameter for this spontaneously broken symmetry. And it has a vacuum expectation value related to the quantum dimension. So this is another way to see that we have spontaneous symmetry breaking. And because this spontaneous asymmetry breaking is coming from a non-zero VEV, we have to do some finite perturbation of our theory to bring that VEV to 0 to disorder the phase. So this thing is robust to local perturbations. Okay, so I'm just telling you things about Chern-Simons theory and quantum Hall that you already know, but telling you that there also exist in some kind of Landau theory, some kind of higher Landau theory. Okay, so let's talk a little bit about the anomaly. If we were to gauge this symmetry, it would be equivalent to dividing A by K. Of course, this is not a kosher thing to do in general because our Dirac quantization condition, which says that the integral of dA over any closed surface is a 2 pi integer. Now it would be a 2 pi over k integer in general. And well, if we just keep track of where the Dirac quantization condition fails, that will be a Z mod K2 form, and that is our gauge field for this gauged higher symmetry. So if you gauge a higher symmetry, you get higher form gauge fields. So here we're gauging a 1-form symmetry, we get a 2-form gauge field. Okay, this theory, if we just divided A by K everywhere, the Chern-Simons action is quadratic in A. So we would end up with a U1 level 1 over K theory. And this theory is problematic. If I try to use this trick for defining the integral, I find that it will depend on the form manifold that I choose. So because I've realized this as going from a theory that was fine to a problem theory by gauging some symmetry, this is a 't Hooft anomaly, and I can study this 't Hooft anomaly by some 4-dimensional topological field theory. Okay, so this. Sure.
This field is charged, is coupled somehow to charges that impose the resistance of the U1 gauge group. Otherwise, how does it know that it's compact?
Well, just like in the statement of the problem, I say I have a U1 gauge field. I need to use compactness to define the Chern-Simons term.
What?
I guess, yeah, I don't need to. But I don't know. Somehow in physics, it's always compact. So I use compact gauge fields.
For some reason, because it couples to charged fields, the charges are quantized, and that quantization imposes the compactness of the group.
Yeah.
It's a dynamical feature of the theory. If you don't have them, you could do whatever you want.
Yeah, R level 1 over K totally makes sense. So there's no, if you have non-compact fields, there's no quantization condition on K,
right,
which is what I'm violating when I gauge this symmetry. So you're right. If I don't use U1 gauge fields, then I don't have this anomaly. But here I'm using gauge fields. Okay. So what is the anomaly theory? Well, now I need to tell you what a local symmetry transformation is, and then that's just a shift where lambda is no longer locally constant. It's no longer flat. Okay. So you can just do this computation on the back of an envelope, and then guess what the 4-dimensional theory is. It's one of these BF theories. Okay, it will be the generator of BF theories in that dimension, the root phase of the topological twist. So it has the non-trivial twist. It has to, because it's a non-trivial anomaly. Okay, so I want to get to another interesting application of this, maybe something that we didn't know already. All the things that I've told you so far are easy to understand if you already figure out what higher symmetry is, so I claim no originality in being the first person to have thought of them. No doubt Anton knows all of the things that I've said. But now I'll tell you about some new work that I'm doing with Max Metlitsky. So if we consider this theory of the 2-component complex fermion in 2 + 1 dimensions, coupled to a gauge field so that it's charge 1, this theory has all kinds of problems. For example, if we try to regulate it with Pauli-Villar's mass, another field, and then we try to integrate out those fields, that will induce some effective action for A by the parity anomaly. We will get this k equals 1/2 Chern-Simons term. So again, we have this problem that U1 level 1/2 is not well defined. Well, one way to fix this, which like you saw in Denson stock, is to just add a k equals 1/2 term to the Lagrangian. Well, that's fine. This term isn't well defined, but this term isn't well defined either, but they cancel each other to make like a level 1. Well, depending on the sign of this mass, there's a parity anomaly. You can either get level 1 or level 0.
In there.
Yeah.
There's 2IA mil.
Yeah, there's.
It gives you well-defined transforms.
Yeah, I'm about to be there also. So let's see. My problem with this term is that it explicitly breaks any orientation reversing symmetry. For example, time reversal, parity symmetry. So I don't like this. I want my theory to be time reversal symmetric. Well, OK, yeah. Now I'm going to put in a 2, because I know that this theory is fine. Here, I can regulate this thing, and it generates a level 1 Chern-Simons theory. Fine, parity anomaly parity symmetry has a ABJ anomaly. I'll deal with that in a second, but at least the theory is well defined. So now that I have this 2 here, now my theory has a higher symmetry of the form I just discussed. So if I shift A by someone whose Wilson loops are only plus or minus 1, then a charge 2 object will never see lambda. It will see either 1 squared around a loop or minus 1 squared around a loop. Never sees lambda. So this is a symmetry of the theory. And it's also the symmetry of any sort of Maxwell term or other things that I would add to this. OK. And I just told you that gauging the symmetry is like dividing the gauge field by k. Here k is 2. So if I divide a hat by 2, I get a. So great, I can gauge the symmetry to get into the problematic theory. So now I've understood the problem with the other theory as some kind of 't Hooft anomaly for this one-form symmetry. I told you before what the anomaly theory is. I'm going to have to modify it in such a way so that things are t-invariant. But for now, I've shown that this thing, QED3, can live on the boundary of some higher SPT, some 2 SPT. With some massaging, so I want to include time reversal invariance. Well, in the 4-dimensional theory, that will also be an orientation reversing symmetry. So a topological term like b squared will go to minus b squared. Well, everything is mod 4. So minus b squared is the same as 3b squared, right? And if I separate this into b squared and 2b squared, now I can use this wonderful property of the second Stiefel-Whitney class that b squared equals bw2 mod 2. This is a wonderful property. So I can say b squared transforms to b squared plus 2 bw2. OK, so that means b, in order to deal with this, b needs to transform under time reversal. And so under time reversal, the Dirac quantization conditions of my gauge field are changing. So b goes to b plus w2. That will also introduce a term w2 squared. On a spin manifold, that's totally fine. On a spin C manifold, you can also cancel it. And then my work with Max right now is like we should really be able to define this on like non-orientable pin C manifolds. So you should see something about that soon. So given this, everything is explicitly t-invariant, well-defined. I can compute the partition function, so I know I'm on the boundary of the TI. Everything is well and good. OK, so here's my summary. If you think symmetries are useful, you should also study higher symmetries. They're not that mathematical and scary. Basically, anything that symmetries can do, higher symmetries can also do, but with more interesting topological character. Some of our favorite things can be re-understood using higher symmetries. We can use higher symmetry as a sort of like charge replica trick, like I just did, starting with a theory with charge 2 objects going to a theory with charge 1 objects and studying that gauging procedure. And some challenge for all of you is to understand the quantum Hall higher symmetry microscopically, or perhaps they don't exist microscopically, perhaps they emerge in the IR. Well, we'd love to understand that. Understand the role of these non-invertible symmetry operators in non-abelian phases. In non-abelian phases, not every quasi-particle has a tensor inverse. So they still make operators that commute with the Hamiltonian, but they're not unitary. So it's kind of strange. And then, of course, solve the representation theory of D groups, solve the representation theory for higher symmetries. And then we'll know when we have a higher symmetry, what are all the quantum numbers that we get to help understand our problem. Okay, thank you very much.
Question?
Yes. In standard Landau theory, one of the advantages was that you could have some mean-field description of the phase transition. Is it possible using this Landau theory for higher symmetries to solve some classical equations and get mean-field critical exponents?
Yeah, so that's a fantastic question. If we could do that, it would surely be the theory for like the confining deconfining phase transition, which is very hard to understand. Yeah, I would love to understand that. Here, like in Landau-Ginzburg theory, the great thing is that your order parameter is just a point operator, right? And so I can just write some effective action for phi. But here, my order parameter is a line operator. So my Landau-Ginzburg theory is like a string theory. Think about that.
Do extensions? That's the problem.
Well, here, so if I talk about like Maxwell theory, it's easier to understand. So the order parameters are like the Wilson loop and the 't Hooft loop, and the different phases have to do with the like large radius characteristics of these loops. So to have a theory that by some interaction of these loops causes either Higgs phase, causes either like Coulomb phase where like the Wilson lines have some large radius expectation value, or like confining phase where the 't Hooft lines have some large radius.
This question is important only if you have second order phase transition. Are there cases where there are continuous phase transition where you need the theory?
That's a great question. I wish I knew how to study that. I'm very interested if you want to talk about it more.
You have a two form, Z-mod-K, two form that you wrote down.
Mm-hmm.
Do you know any examples where instead of Z-mod-K you have a non-abelian group? Two form non-abelian symmetries where even if it's a discrete non-abelian group?
Yeah, so you have this issue that pi 2 of any topological space is abelian. So it's very hard to define non-abelian two forms. The way to have a non-abelian higher symmetry is to have both a zero form, an ordinary symmetry, and one of these higher symmetries. And you can do it in such a way that domain walls for your ordinary symmetry, certain defects there, source fluxes in the other symmetry. And you can also do it in a way that if you bring one of these domain walls around one of these guys, then you have some non-trivial action of the zero form symmetry generators on the one form symmetry generators. So you can make things non-abelian in their interactions between the different forms, but the forms themselves can't be non-abelian.
So if I wanted to understand what a higher symmetry is without using the language of forms and field theory, is it just I have a Hamiltonian, and if there's a loop operator in the space that commutes with the Hamiltonian, you'd say there's a higher symmetry?
That's right.
And you don't require those operators to form a group structure.
Yes, well, automatically by being topological, they will form a higher group structure, or they will perhaps form the structure of like a topological sector of your theory. So So symmetry equals topology. You find a topological sector in your theory, then you study all the representation theory of that, and those are all of your higher symmetries and all of your quantum numbers.
Is there a Coleman-Mermin-Wagner theorem for two?
Yeah, absolutely. Is that the one where you only have 0 temperature phase transitions, or is it the one where when can they be?
The dimension where you can't have long-range order, quantum essentially.
Yeah, so absolutely. So this 2 + 1 dimensions is the critical dimension for these codimension 2 symmetries, and that is by an argument that we're already familiar with, which is since the operators are point defects, if our symmetry is spontaneously broken, maybe they have some mass or something, well, they're entropically favorable as soon as there's any temperature. They just proliferate everywhere. So this symmetry breaking in Chern-Simons theory is just a 0 temperature thing. In Maxwell theory, it persists to positive temperature. So yeah, this paper by Gayotto, Kapustin, Seiberg, and Willett discuss this. But it is much the same argument, just with a different codimension of operator.
Some orders which have same higher symmetries but different something else.
Same higher symmetries but different. Certainly. So there's a whole theory of SPT phases protected by higher symmetries. This one thing I've done here is re-expressed the TI as a gauged 2 SPT coupled to some fermions. And this gauge 2 SPT has some non-trivial topological term. I could also look at a 2 SPT that has a different topological term. So they would have the same symmetry, but different looking ground states. They wouldn't be connected by local unitaries.
Is there a way to go to even higher symmetry potential?
Yeah, absolutely. But for 3 + 1D, 2 forms are the only thing that are important. So if you have a 3 form that participates non-trivially in some topological action, it tends to be that your partition function here, which is the dimension of your state space on S3, this will tend to be 0. So it's not good. So then if you have a 4 form, then this one tends to be 0. It's also no good. So perhaps in some exotic infinite dimensional theories, you can have this kind of thing. But I think for the physical dimension, you only have to think of 1 form and 2 form. The string theorists, you can think about the 8 form symmetries. And they exist.
So you discussed the gauging on the surface state.
Mm-hmm.
What happens if I gauge the symmetry in the box? You have a B field that you described. So you gauge the symmetry in terms of D.
Yes.
What happens to that?
So in general, you will see something like, if I'm drawing a 3-dimensional picture, the B domain walls won't be walls, right? They'll be lines. And those lines will end somewhere on the boundary in fluxes of some sort. It depends exactly what the symmetry is, but you will have this proliferation of codimension 2 domain defects. And yeah, I'm just thinking here about regulating Twift anomaly. So that's exactly the situation I'm thinking of is what am I going to put this thing on the boundary of so that I can gauge the symmetry everywhere and get some gauge invariant thing.
The gauge theory has some domain walls. Do they have some statistics or something like that? The original theory is more normal than the gauge theory.
Yeah.
You gauge it.
Mm-hmm.
You have these domains.
Mm-hmm.
Do they have some statistics or something?
Yeah.
It's related to the boundary.
Well, you should think about Levin Wen on the boundary of Walker-Wang or something like that.
Like that.
Yeah. That's pretty much what this is. So I don't know where I'm going, but the...
Yes, you have the theory in the book, but no gauge.
Yeah, but I could gauge it, and that just means sum over all the B.
Right, yeah.
Since the ground stage is your inner C, you go from one representative ground state to some other representative ground state by threading one of these one of these loop operators around a non-trivial cycle. Is there any hope in trying to understand like most 2D topological phases that way, since all of them have that feature where you go from one ground state to another by threading some loop operator?
Yeah, so I tried to learn about this in the non-abelian case. So for modular theories, it seems like the answer is probably yes, that you can get all of the ground states by threading things. It seems like adding non-abelian character to the theory only decreases your number of ground states, so it's only introducing like more kind of anomaly going on. But I haven't worked that out.
Last question before lunch.
I was wondering if you could give an example of some kind of system where it has a higher symmetry, but the higher symmetry is not broken in the ground states.
So these SPT examples.
So there's a lattice Hamiltonian physics?
Let me just write down a ground state for you. So this thing will have to live in 3 dimensions, and there will be link variables, which I'll call lambda, right, in Z2, is 0 or 1. And then we just consider the sum over all lambda of e to the I integral over space, which is 3D, of, say, lambda d lambda. So this is an example of a ground state of a non-trivial 2SPT. So in this theory, this can be the ground state of some like energetic Hamiltonian. It's kind of easy to invent if you stare at it long enough. There's unique ground state. This state is symmetrical. So the symmetry acts by lambda goes to lambda plus alpha, where d alpha is 0. Okay, so this term is invariant. The variation of this term is going to be alpha d lambda. If x is closed, here we're in SPT, so x has to be closed to be invariant. We integrate by parts and get 0 again. So this operation just permutes this sum. But if we're to gauge this thing, then we get one of the non-trivial elements in H upper 4 BC2 U1. We get the double of the thing that I need to understand the TI. The other thing has like a, well, here I meant to write I pi. The other thing has like a half, but then you have to do more work to add other terms to make it symmetry invariant. But this is like the state to always think about. It's very simple. Yeah.
Okay, so let's have lunch. And thank you for the interesting talk.